Hello, everyone. Thanks for taking your time and making yourself available here. So my name is Arun. I'm from eBay. I'm the product manager for the data platform team. I've been at eBay for 3 years, working mainly on the Hadoop platform area. So just to give a quick overview of what I'm going to talk about, along with Edward, who is the architect from eBay, and he has created a lot of monitoring systems for eBay. And our focus mainly now on Hadoop and how do we monitor Hadoop data platform, and how do we secure the data that's there in Hadoop platform using monitoring as one of the solution. So So just a little bit of background of how we started with Hadoop. So how many of you were in a session earlier today, the talk by eBay folks? Were anyone? Okay, there are a few hands. I'll still go through some of the brief history. So we started with Hadoop like 6 or 7 years ago, and it was like a 20 nodes Hadoop cluster. And it was basically a research team who was trying to use Hadoop for different workloads, and they were like having lots of data, but there was no like really production use cases. But today, over like the last 6 years, we have grown to around 8,000 nodes across 7 Hadoop clusters at eBay, and some of them clusters are for online purpose, meaning they serve the ebay.com site, and rest of them are from the analytics workload. And today we have around like 120 petabytes of data. Actually, this data is from like Q3 2015, so it might be like 150, 160 right now. And you can see like the data is growing, and all our Hadoop clusters have been like growing exponentially. So it is really important for us to answer some of the questions about who is using this data that's there in the Hadoop cluster. And what are they using it for? Are they copying data? Are they writing queries and then downloading data to their laptops and making some reports out of it? So these are the questions we wanted to answer for our InfoSec guys, because they always ask questions like, is their Hadoop cluster secure? Oh, what do you mean by Hadoop clusters being secured? It's like a really huge, like 180 petabytes. Like, how do I even know that the data in the Hadoop cluster is secured? So some of these questions that we had. And how do we get all this data? So we have around like 800 million listings on ebay.com site at any single point of time. So that could be image data, that could be data about the product's pricing, but also about 200 million users who are using eBay to buy products, and also 25 million users who are using eBay to sell the products that they have. So all these interactions that they have with the website or with their mobile app gets recorded. You could imagine like people clicking, people moving, browsing, like going up the page, scrolling down, searching for something, clicking on a search results page, and then watching an item, bidding an item, or selecting an item, and then waiting for like 5 days to see if the price is going to drop, and then like buying it in order to ship it. So all these interactions get into HDFS. So this is our main source of truth for any analytics, and then we also have Teradata for certain kind of reporting. And with all these like big data problems, we also saw like there are 800 million HDFS operations in one of this cluster on a daily basis. And today it could be even like 1 billion access events. So what are these access events? If a user is submitting a Hive query or running a MapReduce job, basically they have a lot of file read operations or write, or they are querying a table or querying a particular column in a table or creating reports. So all this actually translates into HDFS operations in the logs. So how do I, as a user or an InfoSec, a person with InfoSec background, have to go through these 800 million access events and tell which ones are okay, which ones are an anomaly, or is there even a security threat to my Hadoop cluster? So the way we started was we had this Hadoop cluster, we had all this data, people started using it. There are 1,500 employees today at eBay using Hadoop on a daily basis. And then we thought about, hey, let's go and secure this cluster. So it should have been the opposite way. So if you guys are starting this journey, start with like a small cluster, make sure it's secured, and you have different kind of security mechanisms, and then move on to something big. So the way we think about security on Hadoop is under these 4 areas, right? Starting with authorization and access control. So our clusters are secured with Kerberos authentication. And even in order to get into the cluster, you got to go through a couple of hops. For example, we have a gateway machines where people usually log into those, SSH into those machines, and then From there, they have to go through Bastion servers, and then they get access to the data that's there in the Hadoop cluster. So if you have to copy data outside, it's a tedious process. You have to do multiple hops, but they could still do it. And for perimeter security, we have firewalls around all these clusters. So some of these clusters hold PII, PCI data. Some of them have behavior data from the users. So, but each of this data has like really good firewall rules where we make sure folks who are accessing from one zone, usually their laptops are in the corporate IT zone. When they access to Hadoop cluster, they have to go through certain firewalls, and only certain kind of ports are open between those firewalls. So we are pretty much strong there. The third area is the data classification, which is very tricky because when we started with Hadoop, when we said like, okay, users can move all kind of data to Hadoop, and our team helps loading some of the important data sets for eBay, which is around 60 or 70 petabytes of this data comes from the pipelines that we manage and our partners manage. But then the rest is more like our Hadoop users kind of like bringing their own data sets, which we are not aware of. Because each one gets a quota, and then they can bring around a few terabytes of information into the cluster, work with merging those two data sets and play with it. So the data classification was a real big problem when it comes to classifying the data that we don't know about. So we partnered with a vendor specific tool for this particular functionality. What they do is they go through each and every data set that's available in the cluster and match with some pattern matching, and they do some really smart things to identify, okay, you know what, this looks like an email, this looks like an address, putting it all together, it looks like it will give out information about the user, so we got to go protect it. So once you classify the data, okay, for the first three things you took care of it, but still, if I ask you the question, is your cluster secured, I would say I don't know because I'm not monitoring anything that's happening in these clusters. So that's why the activity monitoring piece we're going to spend time on explaining today. So some of the motivation behind this problem is some of the questions that our InfoSec team came and asked us. Give me a list of users, what data sets they're accessing. Is there someone who is trying to access data that they don't have access to? For example, if I'm from a finance team, actually opposite way, if I'm from the marketing team and I suddenly access a financial data set that only a finance person should have access to, and I'm trying to write Hive queries or MapReduce jobs to access that data set, is that kind of a thing happening in your clusters today? So, and then again, it all comes down to, is there a security threat? Is there an anomaly? If there is, am I getting notified? Are those things getting monitored? And there was really no good answer for this before we went with this journey of creating a product called as Apache Eagle, and we open sourced this last year. And there has been like a good response from the industry where there are banks, healthcare companies who are starting to look into POCing the product. So I don't want to go through the definition, but it's basically a monitoring platform which can analyze all the log events that are happening in Hadoop in different access, like it could be HDFS data that's there in Hive, HBase tables, etc., and even Spark going forward. And then trying to identify out of those access events, what are those access events that are an anomaly or a threat or things like that, of that nature. And all this kind of like in real time because the way that we designed the whole platform, we made sure that the whole alerting, identification of a particular problem and alerting takes place within 300 milliseconds for certain alerts. And you can imagine the scale that we are testing it, which is 800 million access events. And imagine if you have 100 policies, you have to go through each of those access events, apply each of those policies, and some of them nested policies in order to get those alerts in real time in a dashboard, so that you can actually go and stop a security threat that from happening. A really good example. So over the last year, there are a couple of incidents at eBay where some engineers from our team or from different teams accidentally deleting data. And this is not like 1 terabyte, this is like 1 petabyte of data. And this happened like a couple of times, not just once. Like one guy 1 petabyte, the other guy's like 1.2 petabyte, and they're like fighting like who deleted most. So the thing is, the first time we didn't identify it, and even the user didn't know that they deleted some data from the cluster, because they wrote a script, and at the very end they were having a command to clean up some of the intermediate data sets, but apparently they used the command with a skip trash option, which is amazing in Hadoop because it's even tough to write that thing because it has a lot of capitals in between, but still he managed to do it. And the guy left for the day. Next day morning, someone else noticed that, hey, I was not able to query particular dates of data. Looking at the logs, it took us some time to even get to the logs, like parse it and identify, oh, there was this mistake that happened. But then the data is gone, like there is no backup. Because Hadoop itself, we thought like, hey, there are 3 copies of data. You don't really need to spend more money on archiving data, backups, etc. But anyway, how do you catch that event? What if like someone else with a malicious intent has access to your cluster and runs a skip trash command over the data that they want to cause harm, right? So how do you identify it? So with Eagle, that was one of the use cases that we want to catch these kind of events and anomalies and really stop that user from finishing that action. So anyway, in this slide, what we were talking about is from the data activity monitoring side, we focus on HDFS Audit Log, Hive, HBase, Cassandra. We want to like also support MapR as a data source. So, and imagine this we designed it for Hadoop data sources, but you could apply this for any data platforms, right? So prior to Eagle being used as a security monitoring, we were using Eagle for monitoring our cluster itself, like the performance of the applications, like MapReduce or Spark application or Hive queries. So how do we do it? Like we collect all the metrics. I will go through this later. So the things that we're working on is also Spark is kind of like catching up. There are a lot of users who are migrating to Spark workload, and there are about like 20% of our clusters are used by Spark workload. So how do you monitor Spark jobs and run them efficiently, right? So Eagle as a monitoring tool can also give suggestions of like, hey, you're running your job with bad parameters, your job, certain tasks are taking too much time, you're not splitting your data properly. So it will give you recommendations on how to do certain things. Sorry. And actually more integrations with supporting all these data sources, like you can monitor access from MongoDB, MapR, as I said, like on Cassandra databases. So one of the other things that we made sure was we made sure that we design Eagle with extensibility in mind, meaning you can take Eagle as a platform or a product and then apply it to different data sources and also integrate with your own monitoring solutions if you have one. For example, like with DG Secure is a product from a vendor, Data Guys. They are doing the data classification for Hadoop. So how can you take the data the classification of the particular data set and then apply it to create policies in Eagle to get alerts? So if you have a metadata repository with data classification, you can actually hook into it and then say, hey, use this classification and I want to create policies on top of that. So with Splunk, so for example, eBay uses Splunk very heavily for site monitoring and different purposes, like all over eBay. And so what we do there is we do the first level of aggregation. We don't ship petabytes of logs into Splunk, whereas we do the first level of aggregation and say, send only the actionable alerts to Splunk dashboard, or if you have any other third-party dashboards, you can just send it to the monitoring tool and then have some security personnel interact with that alert and take actions. So this is complicated, right? I mean, like any other Hadoop architecture diagram, we have one too. And from left to right, if you look at, like we have support for a bunch of data sources, like we consider HDFS, Hive, and any kind of logs that you can imagine, right? And then we consider it as a source. And then how we collect all this data through Kafka, and we do all the processing in Storm. And we are also looking at other technologies now, because in Hadoop area, right, today there will be Storm, like next day there might be something else. So you got to like know like what is the difference between these technologies. But we are staying with Storm because it is good for our use case. And there is also a machine learning part to it, which I'll come back later through the presentation. So once, for example, once we collect the events that are happening in real time and the policies that you as a user enable using the dashboard will actually apply, and we compare each of those events with the policies to generate the alerts. Once the alert is generated, the alert goes back to HBase as a data store. So all the alerts which are generated and the metrics we have collected get stored into HBase. And you can actually use MySQL to store that. But if you are in like petabytes of data, then maybe MySQL is not the right thing. That's why we are in Hadoop, right? So with that, I think I will ask Edward to talk about some of the more technical details.
So I would like to talk a little bit in depth of this architecture of the ego. So why do we invent an ego from the beginning? We also evaluate other traditional monitoring tools like Zabbix, Ganglia. So I know most of our company use the Ganglia to monitor Hadoop, but the problem is in terms of the scalability, right? Say, for example, HDFS Audit Log is like 800 million events per day. So Zabbix is not that scalable for that. The other thing very important is that Ganglia or Zabbix or other traditional monitoring tool, they assume that your data is already prepared. Your data is metric data, contains dimensions and measures. But in fact, that's very that assumption is not correct. For example, in Hadoop, you need to collect the HDFS Audit Log. It's not a simple work. You need to collect the Hive query log. So I don't think that's a very straightforward way to collect the Hive query. So that's why we invent time to evaluate a new system, which is ego. So the first thing we start from ego is ego need to have the capability to streamline the events, stream coming, and you need to do some pre-processing, and you need some policy engine. So look at the middle part and the yellow part. We actually have a policy engine. We can say policy engine today is used as the library, right? We actually use the CP engine to do that. Why we select the CP engine is because that's different from the traditional monitoring. We actually need very comprehensive expression to express our needs for the monitoring. For example, you need a group by, you need a window, you need a slide window to do the alerting. When something exceeds the threshold, you need to generate the alerts. So that's pretty different. So another example is we have a state management in policy engine. That's what today we are considering. Because, for example, if you have a rule which have a window of 1 week data, so when your node fails, then you lose everything. So how do you handle the state management of that? So we can go through a little bit on the highlights. First one, we want after you install the ego, you can have immediately get the audit log, get the Hive query log, so you can just write the policy against those logs. But today we're still a little far away from the turnkey integration. We still need a lot of manual work to integrate HDFS Audit Log. But another thing I just say, we need a very comprehensive rules. The rules is something like event A happen followed by event B. So that's why we select the CP as our first class citizen rules engine. So most important stuff is we want hot deploy rules. At the beginning, we create the ego, which we have a hard-coded rules. We have put that in configuration, but that's not working. So what we do is we hot deploy the rules. Today we select the Storm as our processing language. We deploy, we can hot deploy the rule within the Storm. So that user can create many policies as they can. So we also keep in mind that the whole ecosystem should be metadata driven. Metadata means, for example, how do you modeling your event? The event model is like what fields constitute your event and what type for each field. So that you need to describe your event before you monitor this event. Another metadata is like you have the policy, right? You have you need to monitor multiple sites within a company, so you need to have site as well. So extensibility is also important because Ego cannot succeed alone. So we say, for example, when you generate an alert, how do you do the policy enforcement? So that's why we connect to like Hortonworks Ranger to do the policy enforcement. When alert generates, then we can block the user from access the resources. The last one is that that is not good because we use a monolithic storm topology, which includes data pre-processing and also the alert engine. So that we also collect some feedback from the community that alert engine should be a platform, meaning you should decouple the business logic from the alert platform. So any user can put the data into alert platform. So with that, you can easily do the correlation. So that another thing we need to talk about is traditional monitoring tools does not care about correlation. But within Hadoop, you need a very comprehensive rules. That means at the beginning, you need modeling two different event streams. Then you can write correlation rules. That's relatively supported by CEP engine, any CEP engine like ASPA or CD CEP engine which we selected. So you can join the two event streams. Let me give you two examples we do for Ego at the beginning. One is HDFS Audit Log monitoring. The other is Hive query log monitoring. After that, I will talk about the alert engine a little bit. So this is pretty straightforward. The HDFS log come into Ego, and we partition the stream all the way by the user. Because at the beginning, we believe that our major use case is that we want to monitor users' behavior. So we want to make sure users' data is always time ordered. But that's probably not true. In the real real use case, sometimes you want to say that which command. So say, for example, if you want a rule like a delete command, how many delete command happens within the last 5 minutes? For example, if the number exceeds 1,000, then we trigger the alert. So that means if we partition the data by user, then you cannot do group by command. So that's what the next thing Ego will tackle. So another interesting thing is we have sensitivity metadata join. So like Arun talked about earlier. So in this system, in ecosystem, you can browse your HDFS directories file systems, and you can manually mark which file is sensitive or not. So that way, when the event comes in, if the file is sensitive, then Ego will automatically tag this file to be sensitive. So that way you can define your policy. Say if users access some file sensitive, then you generate an alert. So another way you can import the sensitive metadata through Ego API. That's also possible. So we partner with another company. They can scan the whole HDFS system and find out what files contains the sensitivity data. So that way you can import the data batchly. Another interesting thing is for HDFS Audit Log, what you see from the HDFS Audit Log is actually not the original user command. So that's why in the ego we have to reassemble the command. For example, if you do the command like a copy from local, it's actually generate like a 5 to 6 million commands. So we need to reverse engineering to get the user command back. So in a real system, we get something very interesting is when you partition by the user, right? But you definitely will meet the problem of data skew problem, because in a real use case, some user has a lot of audit logs. Some user probably has a very minimum data. So when you partition by user, it looks like you can achieve the load balance, but actually it's not. So from this screenshot, you can see that maximum and minimum data is like 32 times different. So that's why we also write some custom field grouping in Storm to make sure that our user partitioning is approximately load balanced. So that's one problem. The other problem is computation skew problem. So in the system, one is to, the computation is to evaluate the policy, right? The policy is some expressions. So from this screenshot, you can see that some policy is pretty light, some policy is pretty heavy. So that's also will waste the resource, right? So that's why you also need to understand how much cost one policy will have. So Hive is another very popular one. We want to understand who access what database and what columns and what tables. So we did the same thing. We partition by the user. We get the data from the Yarn API. From Yarn API, we can in the real time we can get the user. If the user create a job, then we immediately get the job, and we also can get the Hive query and also pass the query to be what database, what table they are accessing. The same thing to HDFS. We also need to classify the data in Hive. So here you can see that you can browse the Hive Hive metadata. You can manually mark which field, which column, which table contains sensitive data, and Ego can automatically detect that if you have that policy. So before here is like 2 use cases for the monitoring. So that's why you can see that cannot be solved by the traditional monitoring system. You have to buy your own. So the next one is the alert engine, which is the most like a very separate one. So the first one is we run the CEP engine on top of Apache Storm. We select Apache Storm because Storm can do the streaming. The different components can be pipelined, and also another important one is we don't select the Flink or Spark because Storm has very low level API, so Ego can create application framework on top of that. That means within the probably we can go next slides. This is the autonomy of the CEP engine. So in the right side, you can see that we have the policy store, and we also have the metadata API, and the middle side is the Storm bot. We have a policy check thread, which will periodically to pull which policy is created, updated, or deleted. So that way we can, in the bot, we can have multiple policies can be evaluated for the one single event. Each event will go through all the policies. And also you can see here is that we can have multiple bots to handle the policies because we assume that we possibly have many policies. For example, in the HDFS use case, people can write different policies like who delete what file and how many times access the file, like this. So that policy could be multiple policies. So how do we scale that? So one simple way, naive way, is to you say policy 1, 2, 3 go to the first bot. The other 3 policy will go to another bot. So that's also handled by the Ego framework. So let's go back a little bit. So the second one is inject your policy dynamically. That's what I say at the beginning. So we cannot do a hard-code policy. The policy has to be dynamically loaded. So the third one is the scalability. Scale is 2 dimensions today. One is a computation, right? You need to care about how many policies will handled within one physical bot. The other one is the storage. For the streaming case, it is how much events will come in. So normally with the event partition. So extensibility is easy to understand. We need, after generate the alert, we need go to some policy enforcement. So here is the text example of primitives of the Ego. So the first one is the raw event. It's nothing but a raw log, but after the pre-processing, the raw log will convert into the alert event. That's pretty much ready for to be consumed by the policy engine. So the third one is the policy, right? The policy is pretty simple. This policy is pretty simple. It's like a filtering policy, like command equal get file info. So that's pretty straightforward. And the last one is the alert. So that's the 4 primitives Ego operate on. This is the schema. Like I said, in Ego, when you onboard a new matrix, new data, firstly you need modeling your data to specify what fields and what types for each field. So in terms of the policy capability, because we use the CP engine, we automatically get a lot of capabilities. For example, single event evaluation. The second one is most important in our production is the window-based evaluation. That CEP engine provides a lot of very good Windows semantics. So the third one is the really important because sometimes you need to join 2 different streams. So that's why Ego is developing good tools which you can, when you onboard the event, you can say, I want to join the 2 events. So Ego automatically to make sure that 2 streams can come into the same physical machine, then you can write the join policy against them. The fourth one is the policy like a pattern match and a sequence. That's pretty strong policies. So here is some policies we have in production. The first one is the name node have a master node and a stem nodes. We have the lag between the 2. So this expression will say if the lag between the 2 is larger than 100 within 5 minutes, then we generate an alert. So the second one is last checkpoint time for name node. If checkpoint time is pretty behind the current timestamp, then you generate alert. The third one is the name node HA state change. That means if in this case is within 10 minutes, if your state change from one to another one, then we get alert. So that's a pretty comprehensive policy. I don't believe that Ganglia or Dabex can provide such kind of capabilities. So this is example of you define the policy in UI, you define policy using API. When you define the policy in UI, because we already modeling our event at the beginning, so in the UI the system can automatically list what fields to be you can create the policy against those fields. So that's automatically populated. The scalability, we already talked about that. So actually scalability is two dimensions. But that's today. But for tomorrow, if we want Ego Alert platform to be a separate component, then scalability is more than this. Today we scale with the number of the policies and the number of the data. Ego service, that's we at the beginning we use the HBase as our single storage, but at the community, the feedback from community is that HBase is too hard to set up. So that's why we want to change the HBase, change the metadata store from HBase to a relational database. But and also for Ego we don't want to own the storage. So that's why we want the raw data to be stored in the mature the tools like Drilled or Elasticsearch. If it's metrics, then you put into Drilled. If it's log, you put into Elasticsearch. And Ego can do some, because Ego does not provide a lot of chats. That's what we want to avoid. What we want to do is user can create comprehensive policies, then can provide the correlation capabilities. So everything is on backend until we generate the alerts. So that's why we want to focus on this. But today we just released the Ego 0.3, but we do have a lot of limitations. That's why we are going to do another version which is more powerful. The first one is the integration cost is pretty huge. Say, for example, in community, one use case is they want to integrate Cassandra log into Ego, so they have to write code. So that's not a good way, because Cassandra log is pretty much a normalized log. So that's why from next two versions of Ego, then at the beginning you need modeling your data. So you don't need you don't need write any code to integrate the data source into Ego. So another big problem is Ego Alert Engine is not a multi-tenant. As you see before, it is more like you use the library, right? But multi-tenant has a lot of benefits. So without multi-tenant, you have to run a lot of you have to run many topologies within one cluster. So that's not efficient. Also, I just said that event partition, right? Event problem is when you group by when you partition by one field, then you lose capability on group by another fields.
I think we have time.
Yeah, it's running out of time, but that's already pretty much done. In the Ego 0.5, we will have Alert Engine as a platform. You can easily do correlation and management of the alerts. Okay, thank you.
I think we have, yeah, that's it. You can ask any question. Is there any questions? Cool.
Okay.
Thank you.